In this video, we'll talk about how to compare two population means or two different treatment versus control groups using methods based on the t-distribution. So the method or the approach that we take depends on how our samples are connected. So let's say we have a control group and a treatment group that we might want to compare, or group 1, group 2. How are they related, or are they related? If we have paired data, that means that we're assuming that each observation in one of the groups or one of the data sets has a direct or one-to-one correspondence with a single observation in the other data set. One often seen example of this is in medical trials. Treatment before or measurements taken before versus after some drug or some treatment are naturally paired because we have the same subjects. If, on the other hand, we have two groups that are unrelated, so have no direct connection, then we say that our samples are independent. How we approach modeling this data or answering these research questions depends on how the samples are connected. So let's talk about how each of these should be handled. We'll start with paired data because the paired data approach is really similar to what we've been doing already. So I'll let x sub 1i be the ith observation in group 1, x sub i2 the ith observation in group 2. I'll then define the difference as being x1 minus x2. This new difference variable d becomes my variable of interest. That's the variable that we're now trying to understand. Because we now, once we calculate the difference, really do just have a single variable, we can treat it just like we did in the previous section. So we can calculate a confidence interval for the population mean difference. We can do a test for the population mean difference, just like we would have with a single variable. So let's take a look at an example of this. And the data that I've chosen to use for this example is related to textbook prices. So the authors of the Open Intro textbook went to the UCLA bookstore and compared randomly selected books to their prices on Amazon. They did this both in 2010 and then repeated it in 2017. We're going to look at the data from 2017 since those are the most recent textbook prices. So we have the department abbreviation, so anthropology, art history. We have the course number, again these are UCLA courses. We have the book's ISBN, how much the book cost at UCLA brand new, how much the book cost at Amazon brand new, and the difference. So this difference variable is positive if it costs more at UCLA. It's negative if it costs more at Amazon. This more column means something a little different. It's not whether UCLA versus Amazon is more expensive. It's whether the textbook itself was more expensive in 2017 versus 2010. So looking at the summary statistics for these, the average book price at the UCLA bookstore is about $72. The average book price at Amazon is about $59. Now, as you probably know, there's a ton of variability in textbook prices. Some books require short novels, small books. Some courses require very large books. So let's pick on one of these books. This is Bayesian Data Analysis. This is the 3rd edition. This textbook happens to cost $78.35 at UCLA in 2017. On Amazon in 2017, this book cost $64.09. So the difference would be, what do you think? The difference is going to be positive because the book cost more at UCLA than it did at Amazon. It probably wouldn't make sense to compare this Bayesian data analysis textbook to the Principles of Physics What we would want to do instead is compare the principles of physics at both stores, which is, again, more expensive at the UCLA bookstore. So to make our comparisons make sense, we'll compare each textbook directly. So we'll calculate the difference between the price at UCLA and the price at Amazon. This has already been done in our textbook, or in our data set, excuse me. So we've got the mean difference. On average, the UCLA price was about $12 more. We have the standard deviation. We have some quartiles. So negative differences here. These are again going to imply that the book is more expensive on Amazon. Positive differences, more expensive at the UCLA bookstore. So let's calculate and interpret a 95% confidence interval for this difference in textbook prices. There's one more thing that we need to do this confidence interval. We need our value from the t-distribution, our multiplier. So our sample size n is 11, so our degrees of freedom is 11 minus 1, or 10. Our quantiles from this t-distribution are 0.975. So we'll plug everything into our calculation and get a result like this. So we're 95% confident that the population mean difference in textbook prices is somewhere between $9 and $16. On average, students can save by purchasing textbooks on Amazon instead of from UCLA. So that's how we'll handle a confidence interval. We'll just treat this new variable like a single original variable. We'll take the paired t-test approach very much like we did in the last video as well, with one adjustment. So we're going to test the null hypothesis that the population mean difference is equal to some specific value, which most of the time is going to be 0. If that mean difference is 0, what that really means is that there's no difference between the groups. The price of a book on Amazon would be the same on average as the price of a book at UCLA. So here's how this test works. First, we'll write our null and alternative hypothesis. Our null hypothesis, again, says that the difference is equal to some value. The alternative is that the mean difference is less than, greater than, or different from some value. Again, we will almost always assume this value is 0. We'll calculate our test statistic just like we did in the previous video, except now we'll base it on the new difference variable. We'll determine the p-value using the t.test function, again based on this new difference variable, and then we'll make some conclusion about the original research question. So using this data, is there enough evidence to show that textbooks are more expensive at the UCLA bookstore than on Amazon? So we'll take a greater than alternative, because if they're more expensive at UCLA, then the difference should be positive. Our variable is difference. Our mu, or our hypothesized difference, is 0. That would truly indicate that books were greater at UCLA. We have a very significant, or a very strong p-value. So yes, there is strong evidence to suggest that books are pricier at the UCLA bookstore on average. Now we do have another option for attacking this data. Instead of calculating the difference directly, we could call each of these variables. So here's what I've done. I've used $ notation in R to take the textbook's data set and extract or pull out the UCLA new variable. I'll then take the textbook's data set, extract or pull out the Amazon new variable. Same alternative greater, mu 0. One additional option is that I have to tell R that this is paired data. This approach is handy if you haven't calculated the differences yet. However, if you do have the differences in your data, it's much easier to just work with those differences directly. So my recommendation is to calculate the difference first. So let's talk about the opposite approach, the independent samples approach. So we'll let x1 represent the ith observation in group 1, x2 will be the ith observation in group 2. We'll denote the sample mean in each group as x bar 1 and x bar 2. Because the groups are not linked, the sample sizes may be different. So we'll have sample size n1, sample size n2. Now it turns out that this difference in the sample means follows a t-distribution, which means we can use a t-test on it. The wrinkle comes with the standard error. So how are we going to calculate that? Depending on what assumptions we're willing to make, there are actually two choices for this. So our first assumption is that the populations have the same variance. Variance, remember, is the standard deviation squared. So if the two populations have the same variance, they then have the same standard deviation. If that's true, we'll estimate the standard error using what's called the pooled standard error formula. Details are in your notes for how to calculate that. We will set var.equal to be true. However, if we're not willing to make that assumption, we'll set var.equal to false and use what's called the unpooled or Welsh approximation. This then uses another approximation called the Satterthwaite approximation to adjust the degrees of freedom. It's a whole thing. Again, formulas and details are in your textbook if you're interested. All we really need to know is what to use to implement these assumptions and when to make a particular assumption. So, the confidence interval does have a pretty familiar form. In the background of R, it's going to be calculated by taking this sample difference, adding and subtracting some multiple of the t-distribution times the standard error. Here's how we should choose what to do. So if the ratio of the biggest standard deviation to the smallest standard deviation, if that's greater than 2, use the unpooled standard error. What that means, assume that the variances are not the same. This is actually the default option. So assuming that the variances are not the same is what will be done automatically. If this ratio is less than 2, you can reasonably assume the population variances are the same. So let's take a look at an example. We have a sample of 200 observations that were randomly sampled from the High School and Beyond survey. This is a survey done on high school seniors by the National Center of Education Statistics. Now, researchers want to use this data to study differences in public versus private schools. So we've got data from public schools. These are standardized writing scores. We also have data from the private schools. Notice there's a lot more public schools than there are private schools. The variability in the two groups is pretty similar. Now, looking at the sample statistics, the mean writing score is about 3 points higher for private schools versus public schools. The standard deviation for the public schools is about 10. Private schools is about 7. That ratio is certainly going to be less than 2, so it might make sense to assume that these groups have similar variances. Now, let's see what happens if we make both assumptions. So let's start with the default assumption that the variances for the two groups are not the same. We end up with a p-value of 0.03 when we do this hypothesis test, which is kind of on that border of whether or not we will reject versus fail to reject. At this point, given how large the samples are, I would probably reject a null hypothesis like this. However, if we assume that these populations have the same variance, so if we assume var.equal is true, well, that makes our standard error a bit smaller. That makes our p-value a bit larger. So here, we might make a different conclusion. We might fail to reject. That's one of the reasons why rejecting versus failing to reject a null hypothesis can be tricky. Depending on the assumptions that we're willing to make, we might end up with a different conclusion or a different result. Looking at the confidence intervals that were produced by this output, they're pretty similar. Both of them go at about -6, which would indicate that the private schools have a higher score. They're both ending on the upper point pretty close to 0. So these confidence intervals are telling us that if there is a difference between public schools and private schools, it might not be that big in terms of standardized writing scores. So let's briefly go through the mechanics of this test just to refresh ourselves of the details. Really, the only thing that's been changing is what parameter we're working with. All of these mechanics we should have pretty down pat at this point. So we're looking at the difference in population means. Our null hypothesis says that this is equal to some value, probably 0. The difference in these population means is either less than, greater than, or different from some value. We'll calculate the test statistic. We'll calculate the p-value, still using t.test, and our conclusion will be pretty similar as well. So looking at this, again, we're assuming that variance is not equal by default. We get the smaller of the two p-values. So with this, we would reject our null hypothesis and conclude that there is truly a difference in the population mean writing score for public schools versus private schools. That's it for this video. Look for some homework and potentially some practice problems on Blue Line. In next week's material, we'll start thinking about how to expand this framework to handle means of more than 2 groups. Have a great day.